Okay. Kind of. I did it on my phone. I think it's streaming correctly. Oh, it's not streaming.
They're still there?
Yeah, whatever.
Setting up recording. I cannot log in.
Okay, I think it's recording. I think it's recording, but record it yourself just in case.
Yeah, and should it be streaming on YouTube Live though?
No, because since I didn't I didn't set up the event on time, like the YouTube stream event is set up automatically with the Discord event, and well, with the calendar event actually. So it didn't actually set up the stream correctly, and it's not streaming. But it should be recording anyway, and we can just upload it later. But yeah, record it in your end just in case, because since it's not streaming, I cannot check that it's recording correctly and all that. But anyway, sorry
Okay,
to
I
be
start
Welsh.
recording then.
Let's actually get into the thing.
Yeah.
Yeah, I'll also record on my own computer just in case, and hopefully, like at least one of the recordings should work.
Yeah, let's see. Okay. Topological data analysis and Mech Interp. Yeah. Topology is math that tries to study the number of holes in objects or how
Well,
objects are isomorphic as long as you can stretch them into another object. And
yeah,
without
the amount of holes is the homology, right? That's not really topology, right?
Yeah, I think, and I think topological data analysis also deals with that. Well, yeah, that's when you then start classifying the shapes in different homologies.
Wait, I have no idea about topology, so maybe you can explain things.
Let's try to read and let's see.
Okay, so first, this article is rating a response to a different post. In short, we could also read it, but let's read this one first. This one seems a lot longer. But, okay, no, so this one is just a list of project ideas. That's cool.
Yeah. Let's see
It's
when,
kind
where
of
they
old.
mention topology then.
This post is also old because it's from last year. But, yeah.
Yeah, it's ancient.
Yeah.
By the way, guys,
Already outdated.
let me know if you want me to read parts of the thing. I don't mind doing so if you want that.
Don't worry, I'll just do it myself this time because I have the last time I just was not on my computer, but now I can do
No,
it.
no worries, no. So maybe just we can do like a little bit of you, a little bit of me. I'm open for that, but
We'll
that's
see.
fine. Okay.
Okay, so the article was written in the response to the forum post. Yeah, so some ways to use topological data analysis. Topological using a simple way the internals of convolution. They are doing it in ComNet. You find information about the responsibilities of the various layers as the training process. For LLMs, though, simple approaching with activations raw yields limited insights. Yeah, I'm confused why it works in the ComNet, but yeah.
Yeah, let's see.
Will this could this methodology of yeah. Okay. Term topology refers to the study of shape using methods that are insensitive to deformation such as stressing, compressing, or sharing. For example, topology. Yeah, so this is explanation of topology. Simple names, but you recognize the difference between the digit 0 and the digit 8. Okay, makes sense. Yeah, I do remember at least that much about topology. And all of this.
Yeah, I think there's one nice meme to explain it as well. I'll find it.
And there was this like long video out turning. I think it was a feed into a tunnel or something. You know what I mean?
Say again.
Or well, it was not that sadly. There was a old video where they turn from shape into another shape in an animation that was kind of famous.
Yeah,
But
that sounds topological. Yeah, here's a meme to describe it. You can you can turn all the morning routine structures into these shapes. Yeah, genus 1, genus 2, genus 3, genus 0. I think that's the homology thing.
Okay. Shapes can be represented.
Yeah, genus is determined by its. I mean, the shape is determined by its number of holes.
Yeah, and as far as I know, this only goes for two-dimensional spaces. So like the surfaces of these spaces you see are two-dimensional. We don't have a genus classification, I think, for higher dimensions, as far as I know. Don't pin me on this one.
Locally two-dimensional. Yeah, okay.
Evaluation as a modeling a circle with the understanding that the modeling circumferences with a small amount of error. Shape. Okay, yeah, makes sense. So we have this data set like this, like saying that there is many faults in activations or whatever.
Yeah.
By the way, I want to check my statement that I just made.
Okay, just ask Claude or whatever. So that some LLM's proton-coded features are organized in a circular pattern. Yeah. There's also some things that are not circles, but a lot of them are just circles.
Yeah, circles. My good old friend, circles. Our good old friend. Yeah. Hopefully there are some donut manifolds.
Yes, that was correct what I was saying. This is only for 2 dimensions, just to be. But you can count holes and voids in higher dimension, and that might be interesting for mechanistic interpretability because we expect kind of all the good stuff to happen not in these simpler 2 dimensional
Yeah.
subspaces, right?
Yeah, the issue though becomes that most topological approaches, so like even persistent homology, so on and so forth, they become heavily computationally intensive, right? The higher you go up in dimensions. So that's why like they've traditionally been impractical. And like even when you go into the space of topological deep learning, where you try to use topological constraints, that also still becomes an issue where at higher dimensions, it just becomes intractable to compute.
Right, right. That's an interesting. It's interesting to know what how you can keep it tractable, right?
Yeah, that would be like I guess the essence of a breakthrough in the field would be better tractability.
Right, so that you can still leverage the power that comes from topological, structure that you enforce, kind of. Yeah, okay.
Yeah.
Okay, this is a tool they use, like Mapper, right? That's so it's is this something this similar to that other framework that we looked at last time? The mechanistic the lens, what was it, transformer lens? This is a similar thing, right? To do what they do, right? Mapper.
Transformer less is just a library in general to do all kinds of, like, to get hooks to do whatever code you want on activations. But yeah, I don't know, this just seems like it's a tool.
Family of methods.
Days in a week, my favorite example of a circle in a lens, and they have it here. Nice.
So Mapper seems like it's a family of methods that use topological ideas to build graphs representing datasets. Okay, that makes sense.
There's this other paper. There are numerous where periodic data is shown as a circle when graphed, notably in dynamical systems like predator-prey models. Yeah, I know the predator-prey model. That's a differential equation for predator-prey dynamics. Related though. I guess when you graph it, you somehow get the shape somehow.
Covering of a set X is a family of subsets. Okay, so it's the nerf of a covering. I
See what
don't.
that is. Let's
Let's
try
look.
to pinpoint this. Yeah.
Okay, so covering of a set, is a family of subsets. Let's have a bunch of sets that are part of X, so that so wait, what?
This is
Well,
is that a disjoint union?
I think this is union. Yeah. I think
Not
this is
sure.
union for all of the sets.
Okay. UI.
Yeah, here it just means family of methods to use topological ideas to build graphs representing datasets. So you input dataset, output is some graph, topologically based, I guess. Yeah. Nerf of a covering.
Yeah, they give you an example there. This is let's try to pin this down. They're not being mathematically very accurate, but that's fine.
Okay. The nerf graph of the covering is the graph. Yeah, so X is a subset of the
Yeah.
union. The nerf graph is the covering of the covering is the graph and whose vertices correspond to the sets which are subsets which together they X is a subset of them. So
I
like
think
they
I,
fully
I
cover.
think I get it. I think I get it. I could give it a try if you want to.
Yeah, you can start explaining it.
Yeah, so if you look at that four color figure, which is all those points roughly in a circle, so the whole thing is your U, your set U, or U0, sorry, U, right? And you have a lot of subsets in it. And
I
now
think
you
the set
want
is
to,
X, but yeah.
yeah, oh, sorry, set X, yes. So covering of set X, right? Yeah, so we have X.
The X
X is the
itself.
big set. And you have a bunch of subsets. They're not disjoint, so they have some overlap. So as you see, the blue area overlaps a little bit with the red area and with the green area.
Yeah, but they cover the whole thing because X is a subset of the union of them.
Yes. And then the nerve would be a graph whose vertices correspond to the sets UI, okay, and where vertices VI and VJ form an edge in N. If UI intersect UJ is not the empty set, meaning if there is overlap between UI and UJ, those are two subsets of our big set. If they have an intersection, meaning they overlap, then UI and OJ overlap. As an example, suppose the set X, yes. So what that means, so you're looking
Yeah, if
to
they overlap, they are connected on the graph.
yes. So now you have, so the blue, the red, the green, and the yellow are subsets. You're making a graph that has vertices in each one of them. That's the thing on the right, the little rectangle on the right with the colored corners. But you can only do that if there is an intersection between them. So this is your way
Yeah.
of discretely approximating a continuous space, which is usually
makes
kind
Makes
of
sense.
right.
Yeah.
So
I'm a
that's
bit
what I
confused. I'm a bit confused if the like U0, U1 to UN are all alone on their own subsets of X. At the same time, where you take their union, then the X becomes subset or the same.
Yeah, that
And the
just
union.
means that the all of the U's like together cover all of the point at that point. Like they cover all of X.
Yeah, because
X
what
can
you're
be
confused about,
smaller.
Bernie, what you're confused about is that we're dealing with a covering of X. So this is a cover. This is a notion from topology. It's a covering space of X. So the U0, U1, UN are a covering. It's a family of subsets, a covering of set X. So what
In
does
this
that?
specific example, or go ahead.
A cover, if you have a space, the picture that comes to mind is if you have a circle and think about above the circle like a spiral that is exactly lying above the circle, then that's a cover of the base space. Oh, let's say base covering. Sure.
You can simply say that here it's just saying that like it's a family of subsets that so that the X is a subset of the union of the all of the U's. That means that all of the U's together cover the entire X. You know, like if you get like all here, for example, it's just saying that if you get all of the four ellipses here and you join them, you the union, you get this. thing where all of the data points fall inside it. So X is which is all the data points is a subset of those. You know.
Okay, wait. I think I see the possible example. Let's say there is one point outside, then subsets. So all these ellipses would be subsets of X
Then it's not
itself.
that well drawn, right? Because like
It's a percent
how to
though.
say it, like if U is a subset of X, it only includes things that are on X, right? So it's not like this big circle doesn't include things that are not the data points. That's really just the data
Mm.
points, I think. Okay. Have four versions for comment sets.
I think I'm being pedantic over the detail here.
Yeah. The vertices correspond to the yellow and red sets and connected by an edge because they overlap. Okay. The yellow and blue sets are not connected by edge because they overlap. Building a graph representation of the dataset by constructing a good covering is a powerful technique. NERP lemmas, which guarantee new advantage about topological events of a space with a NERP was sufficiently nice cover of the space. I don't know what sufficiently nice means here, but okay. By the simple construction, but I'm visualizing some simplistic process or whatever. Of course, the graphs often have many more vertices than the model above. Your graph modeling is part of a higher data setting called topological data analysis. Okay, that's nice. I think I like that this explains all of that stuff because otherwise it could just start talking about topological whatever and we will just be confused. Oh.
So you're just building
Yeah, I
a
guess
graph.
in the
You-
use, you can just have different points that are not in X, and that will also work. I think.
Oh,
And then not
I
work
understand.
because X has to be super. All the U's have to be subset of X. Whatever. I'm gonna skip this. This seems like a contradiction a bit to me. But it doesn't matter.
Why? I think you're
It should
getting
be equals X not is subset. Well, it is like if it's this if X is the same as the union of U's, then it's technically also a subset. But there's or equals.
no,
but
it can be okay. So X
so
equals the I mean the union
like
of views. Okay,
like
it's not
you,
possible for X to have things that are not like for the union of the U's to have more things than X. So it's really just X is equal to
yeah
U, I guess.
yeah.
But
So
yeah, I
why
know
is
what you
there
mean.
not equals and why is there subset symbol or equals? Because that implies there's a possibility for there to be things that are not in X, which is in contradiction. Like, suppose there is an element in U that is like outside,
Yes.
because so that you can allow the subset part without the equals. Then it cannot be the case because by definition all the elements in U are subset of X, so it must be just equal.
But I think this is
Whatever.
a minor detail, and I think they might have written this down because they might potentially consider a like a cover. So you could this idea of coverings in topology. That's why that's phrased like that, Bernie. But I'm not super sure.
Like there is a more general thing that maybe doesn't make them so subset or
Yes,
something.
but what I kind of understand from the rest of that paragraph is that these nerves are a tool of building a graph through your data
Yeah.
with some constraints right? Given above, which the mathematical details might not be 100% rigorous for us right now, but
No, I think right now it makes pretty good sense. Like
right?
just a subset of the data, and then if it's overlapping, you make an edge, and then there's
And
that's how you figure out.
I appreciate Bernie pushing back on that. I mean, a very clear understanding does need, a careful understanding
Yeah,
of the core
I
foundation.
do agree. It's weird that they use this symbol instead of equals here, but there's probably some reason for the the act is based on some more general,
Oh yeah, and don't forget this is just a blog post, right? They may just make a mistake or something.
Okay,
It's
graphical modeling can be used to. Okay,
Let's
but
continue. Let's assume a sequel and let's continue for now.
yeah,
then continue number of statistics. Yeah, so there is a bunch of. So turns out there is some nice lemmas that tell you that. Yeah, I don't know what topological equivalence of a space means in this case, but I'm guessing that its graph is. I don't know what it means exactly.
Can I say something about this? So when you have a topological space, say a donut, you can make a so a graph. You can make a graph. They call it a what do they call it? A not a homotopy. I forgot the word, but you can make a graph that represents that topological space and kind of reduce it down to the bare minimum of vertices of edges, which would be
Ah,
called, what was it?
so if something is represented by the same graph, they are like topologically equivalent or something like that.
Exactly. So it's called, I think, a polytope.
Okay, I think they are just saying here that these nerf graphs also have that if they follow some properties, they two things that represent the same graph are
Sorry, to
equivalent.
for construction show
Okay,
graph.
there are representations for conditional models. Yeah, more vertices. Can use the internet neural networks are related below from this paper. So
Homotopy equivalence. Morphism. I think. Outer characteristic, I think. For 2D surfaces.
Yeah, you can always reduce down a topological space to a graph. And
I think it's outer characteristic. I'm gonna send it in the chat.
characteristic, Euler characteristic. Oh yeah, that's related. It's related, but it's
Drives
not
topological
the Euler.
spaces shape. Yeah.
Yeah, but
Structure.
the Euler characteristic gives you, you can see that it's always 2 for the Platonic solids, but and it can have a value of 0 for certain topological space, and other topological space have even a negative Euler characteristic. But it's just the Euler characteristic is just the amount of vertices minus the edges plus the faces. That also tells you a little bit about the kind of topological space you're dealing with. In our case, I think for the donuts, we always are dealing with, or let's say, no, yeah, actually, so we can, I think, expect Euler characteristic of 2 and 0. I think. So the donuts, starting with 1 hole, 2 hole, 3 hole, have Euler characteristic, I think, 1, 2, 3,
Yeah,
4.
the donut is 0, double torus has 0, double, which is a donut, double torus. So you have 2 holes instead of -2 outer characteristic. Triple one has -4. Triple torus.
Yeah, this Wikipedia.
Circle also has 0. So that would make circle equivalent to torus. This has 1. Sphere has 2. Oval has 1. TV complex. Yes, that's also the
But how did you get at the Euler characteristic, Bernie?
Wikipedia has a list of the shapes.
I'm sorry?
Wikipedia has a list of the shapes and their Euler characteristics.
Yes, but the nerve of the nerve we're dealing with the article.
Yeah, I'm not sure if it uses it there. Okay, let's see some examples. The nerve graph of a
So we're still dealing with actually how do you discretely, describe a topological space from discrete data, because the analytical approach to topology is, of course, not computational. So you have to discretize or even kind of space fit. Is that a term? You were doing space fitting. So I give you data and you fit a topological space onto that data if there is one by doing these nerves. That's what I understand without going too much detail. Kind of.
Yeah, makes sense.
Right. So because you're interested in
spline fitting, space
yeah,
fitting.
spline fitting.
Yeah, that's used in other methods.
Right.
So here it's kind of space fitting. Yeah, I think that's a good term. Okay,
Right.
I'm gonna try to read more now.
Okay.
Nerve lemmas, nerve complex.
Okay, so this is just plotting different division for different layers, or the weight, I think. Yeah, it's okay. The weight.
So you reduce topological problem to graph theory problem then, right? I think. Let's see.
Okay, Burley, do you or someone doesn't even understand like
Slowly getting there. Wait a minute.
yeah, like the next image here, like this.
Yeah, I'm
how
gonna see if I get it.
Uh,
There are
I just
numerous strategies for
on this
constructing graph
paper.
models activated by this
Ah,
simple
okay. This is just this actually the graph. Like it. It's just very zoomed out, and this like these are the points in the graph.
topological data analysis. It's like on its own giant field. It's basically machine learning using topology. As I understand. It's so big that it has its own Wikipedia page.
Mhm.
Approach to analysis of datasets using techniques from technology. That's literally the definition.
Okay, so there are different graphs that you can have. So the nerve of a cover, which we're dealing with this in this article, has no directed edges. But you can also make a graph with directed edges to represent the space.
Wow. Yeah. Directed edge. Yeah, I guess you could do that, but I'm not sure how to exactly determine the direction. I guess that could give you some info.
Well, it's just when we consider the nerve of a covering, we don't we kind of say something about the topological space. with a graph without directed edges. So it's like we can get a circle or a figure 8 or maybe some more elaborate graph, but we don't get edges in those graphs. So it's one way. Maybe you don't get all the information about the space if you would also include the directed graph kind of information, because that would really tell you more. Maybe I'm quite sure. But those pictures here in the article where Victor is,
Mhm.
yeah, that's kind of I don't understand those too much. I would
Looking at these, seems like they are just the graphs from the, they're just very zoom out.
What is the black stuff around it? What is that? The black.
I'm not sure, but I think it's related to this being a convolutional net. They are trying to.
Wait, yeah, but very interesting. So you're trying to
Yeah, I
make
think that's true.
Oh, go ahead.
If you go to the presentation to page 28, you can see how they have like arrow. I think that's the different convolutions. It's the examples of the different convolutions. So they plot it around like this to like show that, oh, actually here's a structure that like the
Yes,
convolutions that look this way are on the bottom,
yes,
convolutions that look
that
this way
makes
are on the
sense.
top, and so on.
Makes sense. Makes sense.
My guess.
But I thought this was weights, so.
Yeah, this is weights. I guess they are like showing it here first for weights, and then they're like, okay, now we do Mech Interp, so let's apply it to activations. That's my guess. Let's see if that's actually
Right.
what's gonna happen.
Right.
The less wrong post.
I think it's probably on the paper. In this topological approach of deep learning.
By the way, quick question, guys. I don't hope to, disturb too much. So, what do you guys know? This is being applied. Are you guys aware of results that use topological data analysis, or are we just interested in it for potential use, or is there
I
some
mean,
stuff going on?
for making Terp, I don't know. I don't think so. That maybe some fire thing. I know that topological stuff is other people use it for things, but for interpretability, I think not much yet.
Yeah, so this is why we're reading this paper to see how actually useful it might be. I am
Uh-huh.
100%, okay, maybe that's too much, 99.99999% sure that Goodfire will make something equivalent to this in the next year. I'm gonna make a money float prediction.
I think that's too high. I will bet against it and take all your
Yeah,
money.
probably. It's too high. Okay, in next 5 years, I think that's good enough.
No. Do bet it that way. Let me take all your money.
Yeah.
Anyway.
Like, this is the obvious next step when you're like working on shapes. Yeah.
But this tool is super handy, not just in, this maybe in mechanistic
I mean,
interpretability.
maybe
but-
it's the obvious next
Yeah,
step, but it's maybe too expensive.
like physics is full of topology as well, as far as I know. Or like there's topology of brainwaves manifolds as well. This is why I thought.
Oh yeah, but
This is another reason why I expect it to be in Mech Interp, because
right,
neuroscientists love it already.
right. But you could also even imagine some of this stuff, for instance, in machine learning, like the article that was shared on MLST recently about the kind of program synthesis directions and
Yeah, I'm sure.
it's just to understand the topology of your space gives you much more handle on these enormous amounts of data, and you can kind of reason about the soup of values instead of having just the soup of values, right?
Yeah,
It's just-
definitely. I'm also now looking at the archive paper. They say they apply it to the computations they're performed? By that, do they mean applied to activations? Do they have some fancy images? Oh yeah, it's the same image. Okay, so the figure 3. That's NIST layer 1, okay. NIST layer 2. So those are the different activations of the different convolutions. For what?
I was going to try to figure. I don't know what is that, but by something I grab it. But I was going to. So this paper should. No, not this one. I don't know. Let's go back to the thing.
This is an ancient Mech Interp from 2018.
Okay. So. Okay, so they do this to prove stuff we couldn't understand, but let's read the whole thing first because yeah, I think we can get to the other paper. We have to read the other paper to understand exactly how they get these plots. But
Yeah, they don't say the word nerve covering at all in the.
okay, so same key analysis for the first layer because for the random.
Yeah, it's in weight space. So it's the convolutions at each layer. So each put together many such weight vectors from 100 separate training runs, and then apply mapper to that collection. Okay. So each point is a different training run at different layer. Then different land filter / kernel in weight space. Just when two clusters share weight vectors because the original boxes overlap.
Okay. So there's a Mech Interp section here. Oh, so this is they are talking about. Okay, so this is Apollo Research already was talking about the. We need to look at about the geometry in es parte de estos algoritmos geometry stuff that Wildfire is working on now.
We constructed, so it's authors of this archive paper. Gunnar Carlsson. Oh yeah, the author of this blog post is the same as the author of the 8 years old
They're working on cross-layer transcoder now. What's the fuck thing? We haven't posted much since lately, but
Can hear you for 10 seconds.
okay. So yeah, so this is just saying geometry is useful. Graph
Do
modeling.
they do any experiments themselves? Graph modeling of essays features. Ah, okay.
Okay, so right on this
Each
particular.
node in the graph corresponds to collections of assay features.
Okay, so okay, so graph modeling of first secondary features. So yeah, sorry, can you set it way?
So, do they, in the assay experiment, do they get assay features, compare the vectors by cosine similarity, group nearby features into overlapping clusters, and then convert those clusters into that graph?
Okay, so they use a variant of the mapper technique, which does the nerve graphs thing. Yeah. The largest component of the graph constituting these features is displayed below. Okay. Okay, so they just use cosine similarity to compare features.
Yeah.
Oh, that's a cool shape. Collection of secondary features. We will go to selections to the so there's like subsets of features and they do this map thing which probably uses the cosine similarity as distance and tries to group them in subsets and try to make a graph with subsets that cover the whole thing, and this is the graph you get. Yeah, I guess this is a cool visualization, but I'm not sure how much.
They talk about how they will share a cleaned up club notebook. I wonder if they ever did that.
Maybe. Hoy tengo que turn around. Ahí sí. Okay, so methodic. So you have this thing. What does this say actually? Connect, link, belong, contribute, refer. Uh-huh. Contrast, position, comparison. So yeah, they have a bunch of features that have the similar meanings.
Indicate what words or concepts trigger the features in each node or region. I guess the plot itself. How do they make the plot? Is it PCA? Is it some other dimension reduction T-SNE or something? Actually, differing frequency.
Yeah, as long as it doesn't have much else, seems like this is just the obvious thing. Like here's they have the collab here. So this is this post is just applying the topological methods to as part of the coders and saying that's cool and not much else.
How exactly did they get the graph?
There is a collab here, so we could look at it. My understanding is they take the sparse autoencoder features and they run this mapper algorithm. Well, it's a family of algorithms, but yeah, it's some variant of mapper for on it to make a graph using the.
I see.
Yeah, so like in practice, there is just a nice
Import
mapper.
solution.
Yeah, there's just a nice mapper function that does it, I guess.
I see.
Because it's you just import mapper and you just run mapper, but as I
Okay.
understanding is the thing it's doing, as I understand it, is using the cosine similarity as the metric. I think the thing it's doing is just okay. So it takes the features, it has them in a. You can imagine the features in some space that where the position depends on the cosine similarity, or like
Yeah.
you plot them in weight space or whatever, and then you use the cosine similarity as the distance metric, and you just do something like try to make a bunch of subsets that cover that graph with probably some nice properties, like maybe only put things on the same subsets when they have certain amount of distance or whatever. We will have to go into the details of mapper, but I'm guessing it's something like that. And then it just when two of the subsets are have overlaps, it just makes a line between them.
Yeah, it makes sense.
Like I'm not sure, but I imagine the thing that makes us thing is something like Camins or whatever, you know. But I don't know what Macper actually uses.
Yeah, I posted in the chat blue light graphs docs. Yeah, this is interesting. And does it give any insights though? If you look at the graph, does it tell you something interesting?
Seems like the different points on the graphs are about specific things, but I don't know if it's the super interesting.
Selection A. So they look at the global graph, then they looked at a subset. Selection A contains a 3-step progression, which looks like this. Regard to attributed to associate link to.
Yeah, I guess maybe if you spend a while looking at it, you could figure something out.
Could you find circles in unsupervised way this way or
I'm going
something?
to run it to see what happens, but
We're gonna try.
yeah, I don't know.
Formulate assailants about AI. Into Python. All three have to do with relationships. Yeah, so it clusters. Well, I'm not surprised it clusters together features that are similar. Oh, right. Guys, more explicit types of relationships. More explicit type. So it's like a manifold with of relationships, and as you go along the manifold, you get more and more explicit relationships. Makes sense. Then you branch into adverbs or something. I don't know. Looks like in an uninterpretable mess.
Yeah, I mean, this version of the method is probably not that useful, but maybe there is something. I think it's still interesting to have read it because maybe there's something that, to learn here for like coming up with better methods for like like the good fire stuff. Yeah, I guess
Yeah.
it's doesn't have much
Section. Okay, so
on the
in
paper.
this
I partly
section
picked it because
B,
it seemed simple and we wouldn't spend too much time on it because I was kind of tired today.
so in the section B, they have a Y shape enclosed in the upper left, and we can interpret it like this: agreements, responsive liabilities, exceptions, or otherwise a rules regulation. That seems arbitrary. I'm not sure if this tells me anything. The B section they show here. Do you see some structure or pattern or something in this?
And this, okay.
This looks like a symbolic astrology. This other one, the section B.
Regulation finance. Yeah, they seem.
This
I
is-
mean, they are all related, right? I don't know why they.
yeah, it's all like
But this is already on
it's
a
all, how do you call it? Yeah, legal stuff. It's
yeah.
all part of
But
legal
this is
stuff.
because so it's here, right? So it makes probably on the legal region of the graph. I mean, it's
Actually,
interesting
it's
that this
interesting
part
that
of the graph it's all about
yeah,
legal stuff. But yeah.
but it's interesting that it seems like the connections are only locally. So the overlaps are only locally like this. Okay, that's actually very interesting. So like you don't have overlap from like. So it seems like. Can you?
I guess, but the question is also
graph
like,
look
what
interpret-
does this kind of thing buy you that you don't get from if you just plot the, the
You get
features by cosine similarity, you know?
you get the unsupervised connections.
Yeah.
So maybe this could make you allow you to do unsupervised manifold discovery. Actually, when I think about it, because if it would recover a circle this
Yeah,
way,
you will need to do it then on. Well, you could. This I expect the manifolds in the thing will be like more lower than the entire thing. Will be more. And this is on weight space. Maybe you want also to do it on activation
uh,
space, and you want
this
to
is
do it.
activations. No, this is essays activations.
Yeah, sorry, you're right. But you might want to do it for just to say if you might do it for specific activations. But yeah, you could find if you have some. Uh, you might need to do it with much higher resolution, some such a thing, to see, for example, I'm guessing you probably don't see the circle for the numbers, for example, here, because it's going to just look like a line because all of the numbers are going to be, this is probably too high resolution because on the entire data set or whatever, you know, for all the features.
I wonder if you
But
could apply to the sparse feature visual. Sparse feature. Sorry, how is it called? The
the sparse model
the
thing,
yeah the good fire e- e- generalization of essays into the manifold.
yeah.
Yeah. I wonder if you could apply it to that instead of essay features. Okay,
The
that's a
block
project idea.
sparse, whatever,
Yeah, blocks, but
yeah,
yeah, exactly.
maybe. Then there's this another method. Oh, here it did. I let it running and it did something. I
Yeah,
don't
I
know
also
why
let it running,
this
and
error
I
moving.
also have this.
It was kind of
Yeah,
a
it's
mess.
interesting how. Yeah, it's also interesting how you have the disconnected cluster on the left. So everything on the left is disconnected and everything on the right is connected. And there is some things which have a lot of connections. 50
Yeah.
thing.
I wonder if this is an artifact of my config. Oh, no. Fastness.
References to political campaigns is the biggest node. This definitely also depends on your data sets too.
Yeah, also interconnectivity. Yeah.
Specific locations and addresses.
You increase the connectivity a lot, it just connects everything, but with zero it doesn't.
I wonder if I tell Claude or Codex something like use this and use the sparse feature visualizers, combine it and find something useful.
Yeah, I mean, I think
Uh,
something I learned from this that mapper could be interesting. I will need to spend more time understanding exactly what it means for the graph to be connected in some way, like what the satellite does, some of that. It seems like an interesting visualization tool to learn about.
yeah,
Like, I mean, on itself, I don't think. Yeah, usually has a thing that explains mapper that is nice
color
on
by
the chat.
density.
So yeah, I'll probably read a bit about that at some point. But yeah, I guess the
So I'm guessing the connectivity parameter on top is like how many subs, how many have to have overlap. So the smaller the connectivity, the more you need an overlap to create a node, to create a connection. That would be my guess. And coarseness is how many features you have in total, right? Or how many clusters it creates, right? So
Yeah.
how big are the different clusters?
You do maximum clustering. What was-
Did you also have a numpy error? Yeah, you do. On bottom, yeah.
Yeah.
Type has attribute numpy. They didn't define spot.
I don't think here about numbers.
They did define sparsity. The SA now returns on SA feature object. Use SA and sparsity to get sparsity. Okay, so I'm gonna quickly fix that. So run all again. This should fix it.
Yeah, I guess that's mostly it.
Okay,
I
if it's not fixed, I guess I will push the. Let's see if this will work.
Yeah, I don't. Yeah, I don't get much. I don't have much else to talk about this. But yeah, topology seems interesting, and maybe these mapper things are useful for something. I don't think we
I
learned.
yeah, I believe you can like. I believe you can find unsupervised manifolds this way.
Yeah, that seems interesting. I think for that you probably want to do something more like instead of taking the entire thing just for some specific sample or something you might want
Yes,
to.
true. Like
Or
just
something.
days of a week. Like what happens if you apply to the features corresponding to days of a week?
I guess we want to do supervised that's less interesting. I guess. How do you do more? I guess just something where you will need something more expensive where the coarseness is like you just don't do this coarseness thing at all. You just take maybe you focus on some subset or something, but you just take all of the make all of the connections with all possible sparse encoder features or something, and you then find interesting shapes on it somehow.
Yeah, but probably you shouldn't do it for every possible SA feature and then see this insane.
Maybe on some
interconnection
data
map.
set or something, but yeah.
Yeah. I think that as well. Yeah, but this is very interesting that it works still, or kinda. Yeah, like the examples are terrible. I'm not sure why they didn't try to do it for do it for some smaller features, not just every single possible feature.
Yeah. This was probably just easier to run. But I guess that's mostly it. Does anyone have anything they want to look at or to do? I mean, we could get into detail of how mapper works, but I don't know if it's worth doing that right now. I'm tempted to just end it early today. I mean, I say earlier, but we used to take 1 hour or something. Now now 1 hour is early.
I might try to read how exactly they did it on the weight space. Obtained from VGG16, a convolutional network pre-trained on ImageNet. For each layer, we constructed a
Right,
data set of weight vectors for each node.
Anyone else has takes, by the way?
Yeah, that's anyone else has any opinions? See Sam left.
Yeah. Understand. Usagi, do you have some take?
Oh,
What can people do?
no. I was just reading the mapper thing that I put in the chat.
Oh, right, that's interesting.
Mapper is
Do you learn
explaining
anything
everything.
anything interesting about how Mapper works?
Yeah, you can look at the figure 4 in that link. You'll see like an example.
Fifth complex.
Okay.
You mean redefined pullback cover? The height function of surface in R3.
How do you right, but it seems to be like if you have some actual real they have a real valued function, right? But on the thing we only have on the dataset we only have some points, but I guess here you're probably picking points from the function anyway. Okay, yes, use the dataset.
How's the upper distance? Which is for fractals now. Stuff cool math I wanna understand.
Anyway, should we end the reading group? Or do we want to do anything else about this paper?
To you. I might try to quickly read how they apply to weight space.
Okay. I mean, I can wait a bit with the recording. I guess I'll wait a bit with the recording before.
So what do they
so
say in the later?
where?
They talk about next steps. Did you look at that?
Oh,
I didn't.
yes. So, okay, we can read that. What is the what is the relationship with the geometric structure? Oh, yeah, forgetting about this. Of feature recorded vector and the geometric feature structure of feature activation on corpus. Okay. Is it possible for highly coactivating features to have these similar decoder vectors? Okay, so features that activate together but have very different vectors. I think I would expect so, right? Or oh wait, not because maybe not because of the way sports encoders are trained. Different powers for model compute similar information, like not necessarily. Like they can be two different concepts that go together, but two different things. But I think you're going to have problems with the sports encoder for that because it's going to want to do an average of both as a single feature. Probably. They are the best techniques that could integrate both processes in a single graph. Okay. Where some features more densely pack in coactivation space than others. The features we discovered were found in this razor data. Is there interesting to project in the less dense razor feature space? Maybe. There's probably on the embeddings you'll find also the like all of the what was the glitch tokens there. A weird corner of the thing.
Collectivation than others.
Is she ever to see a river here? Maybe. Other relationships between features and different models like from today. I wonder if this person did anything new, or like I think they haven't posted that many recent things on Run, but maybe they're working on something with this. That could be cool. Does the sentence coordinates for something like local charts for motivation manifold? Maybe. And we see contestor features working like favor bundle
Oh,
of shift
yeah.
space of more global features. Yes, this is like the good fire stuff. I don't know if you can get anything, how to get that on the manifold, but maybe you can. For the sorry, from the topological stuff, but yeah. Is there a signal in data that indicate the type of pages find hard to capture? Maybe. They say people, they check it or something.
Fiber bundle or a sheaf. Oh yeah. Abstract math. Sheaf, I think it's sheaf. Right? Is like how
Well, they have a thing later.
formalizing using local information to get global information, stuff like that, like vaguely. Systematically tracking data attached to open sets of a topological space.
They have this other post from a bit later that where they look a bit more those things.
Geometry of features.
Uh,
Does this guy work for Goodfire now?
maybe. They haven't posted in a while. Maybe it's just working under the fire.
Wait, is it the same? Is it the same mathematician that comes up working in
On
algebraic
Wikipedia,
topology?
maybe.
Computing persistent homology. What? Is it the same guy? I don't think it's the same guy. No, it is. Position, topological determ deep learning is the new frontier for relation learning. Is this a very, very unexpected same naming? Is it this guy? I'm a bit confused because he
Seems unlikely
doesn't.
that this is a different guy, though.
Yeah, but the archive paper. Wait, okay, let me see the archive paper. Because this guy literally wrote computing persistent homology thing, which is cited a lot.
It could be that he's was doing that and now wants to do more Mech Interp things.
Yeah, probably. Gunnar Carlsson.
I mean, could also be a different guy.
But
Could also
if
be
it's a
like
different guy, then it's like interesting, insane coincidence that it's the same name,
I mean,
named guy
could
doing the
also be
same thing basically, almost.
could also be the song of the other guy. Too.
Yeah, that's true.
They have the same name.
Archive search is useless because it's linked absolutely everyone with this name. Yeah, I think it's the same guy. Yeah, I did a lot of topology. To subscribe to more scientists on Google Scholar and scroll Google Scholar feed. What are the newest posts? Cross-layer transcoders for Qwen3, December 2025. Improving CNNs with plane networks, topological approach to AI.
Also, the video I
About the
was
geometry of
thinking of.
features. Oh. Wait, is this ancient video? Yeah, I think I've seen, not in full, but yeah, this video is ancient. This is before we had free blue and brown level technology. Oh, you muted yourself, but I think that's intentional.
Oh yeah, sorry. It was intentional, but I forgot to unmute.
Okay, yeah. I wonder about the geometry feature paper. The other one, topological models. He also talks about topology there. Examples. Ooh. You can just scroll the shapes on the bottom. Yeah, it shows some clusters apparently.
Oh, this actually seems to be
Yeah, here's
related.
more
Yeah, it's
empirical things.
definitely the same guy because it's
Yeah.
related to his most recent paper was about cancer or whatever.
Interesting that he posted on Less Wrong like this. Yeah.
I mean, a lot of people
DC.
posted this wrong.
Yeah, that's true. It's
Just
not
cool
niche
people posting
anymore.
this wrong. I mean, it was, even if when was is niche, a lot of the kind of people who write paper about topology is also the kind of people who will post less wrong. Also, I don't know,
True.
Wei Dai, for example, also posted less wrong since the start. And Wei Dai like invented cryptocurrency.
Ah, okay. Yeah. Critique concepts. Okay, summary. Okay, let me see if I fix the. Yeah, okay, I fixed the Google follow-up, not really compiling. So there's one more graph there, but it doesn't look that like shows much.
Anyway, want to end the recording and maybe switch to talk about the other stuff? Or want to keep
Ew.
looking at this?
Sure, probably.
Hmm?
Let's end maybe. Yeah, we can end maybe.
Okay, let's
Or yeah.
do that. Move to general. I have some things to talk about. Let's see. Let's stop the recording. I'll also stop the recording on the other side.
Mm-hmm. Yeah, I also stop recording.